Today's lab is going to take a look at the chemistry of alkenes, and it's qualitative test where we're not really interested in measuring how much of a product we get from a chemical reaction. Visually, we're just trying to see if a chemical change took place. And before we get into the different chemical tests, I just kind of want to go back and take a look at the general structure of alkanes and alkenes and aromatic compounds. I could bring in alkynes for these tests. For this particular lab, we're not using any alkynes, but they would follow a similar pattern that we would see for alkenes with the triple bond for that of alkynes. So if we take a look at an alkane, and again, these bonds could be bonded to other carbons or to hydrogens. This is just a generic structure here. So if you remember alkanes, the carbons all connected by single bonds. And generally speaking, alkanes are the least reactive of all of the organic classes of compounds. There's really no particular functional group there because all the carbons are connected by single bonds. We have the double bonds. This carbon-carbon double bond does give increased reactivity to this class of compounds. This is called an unsaturated system, whereas the alkane would be a saturated system. So this double bond is reactive to certain reagents. And then this is an aromatic compound. It is also an unsaturated system, but this particular compound, benzene, and even benzene derivatives for the most part, are fairly non-reactive to the reagents we're going to use today. You can react benzene, but not in a type of addition reactions of which these two reagents that we're going to use today would follow that pathway. Even though you've got multiple carbon-carbon double bonds, there's something unique about that structure in benzene. These double bonds aren't really localized, if you will. They can change position throughout that ring, but they're always going to be sandwiched between two single bonds, if you will. That conjugation, and conjugation refers to that alternating double, single, double, single, double, single bond arrangement, usually makes that aromatic ring unusually stable. So the two reagents that we're going to use today would be bromine, and your textbook or lab manual calls for pyridinium bromide perbromide, typically because it's less toxic than bromine dissolved either in some type of nonpolar solvent. Ours will most likely be in dichloromethane or cyclohexane. I'm going to use bromine and not the pyridinium bromide perbromide. You still get the same results. I'm going to use bromine instead. If we take an alkane and treat that with bromine under these conditions, there is no reaction. And how we would tell whether something might happen, bromine solution has kind of a dark orange color to it. It may be a lighter orange, it just really depends on the concentration. So if I add this reagent bromine to the alkane, that orange color would still stay present, and therefore that would be indicative of no reaction. If we treat the bromine with the carbon-carbon double bond, these pi electrons in that double bond will react with the bromine atoms, and what we've done is simply added the two bromines across that carbon-carbon double bond. In some instances, it may matter whether they're both on the same side or one's on top or one's on bottom. Generally speaking, when bromine adds, it does so in an anti-fashion. Whether or not that makes a difference in the product depends on what other groups are on these carbons of that original double bond. But how would I know that a reaction took place there is that the orange color would disappear, and that would be indicative of a positive test. If I treat benzene with bromine, NR stands for no reaction again. So even though we've got these multiple double bonds in that structure, they are unreactive to bromine in this set of conditions. And the way we would see that, again, no reaction means the orange color would stay. So the other type of reaction we're going to do today is using potassium permanganate. And potassium permanganate is a pretty strong oxidizer. Some people would call this reaction oxidation reduction, which it is, but it's also an addition reaction across that carbon-carbon double bond. Potassium permanganate has a purple color to it when it's dissolved in acetone. So if I were to take an alkane and treat it with potassium permanganate, no reaction, what would I see? The purple color would stay. If I take a carbon-carbon double bond and treat that with potassium permanganate, there is a reaction, and the end result is we form a diol where two OH groups add across that initial carbon-carbon double bond. And notice I put in this structure both OHs on the same side of that original double bond. And usually the OHs, we call it a syn, S-Y-N, a syn addition. They typically add on the same side of that original double bond. What would be my evidence of reaction? That purple color would disappear, and I would form manganese dioxide, which is a brown precipitate. That would be a positive test for a carbon-carbon double bond. If I treat potassium permanganate with the benzene, notice again, no reaction. Visually what I would see was that purple color would stay. So what we're going to do is take several different substances and also an unknown, and then treat it with these reagents, and what that's going to tell us is the type of saturation or unsaturation do I have. So what you'll need for this part of the experiment, you'll need several test tubes. I have more than I need for this one first part that we're going to do. But what I'm going to do is to put several drops of each substance into separate test tubes. I'll do one at a time. Some of these substances may evaporate somewhat quickly, so I'll do one at a time. I'll add some cyclohexane to the first test tube, and then after I do that, I'm going to go back and add some of the bromine that we have here. So I'll add the bromine to that, and what we're looking for, if the orange color disappears, that would be a positive test for unsaturation. So in your lab book, you would need to put what the results from each of these tests would that we see, and then you could tell whether or not it was positive versus negative. So first test tube, I'm just going to put several drops of the cyclohexane, and then I'm going to add a few drops of bromine to that test tube. So here's your cyclohexane. I'm going to add some bromine to it, a couple of drops of bromine. And if you notice, the orange color stays. So if the orange color stays, there was no reaction. And remember, bromine for this particular experiment is only going to react with carbon-carbon double bonds that are unsaturated, excluding those of aromatic compounds such as benzene. The next compound I'm going to try is mineral oil, and the one after that is canola oil. And those substances are fairly thick, so I'm going to dissolve those a little bit in cyclohexane. Why cyclohexane? I know it's not reacting with the benzene, so it will not give me a false positive test. So I'm going to add a little bit of cyclohexane first to the second and third test tube. Into the second test tube, I'm going to add some of the mineral oil. And then I'm going to add some of the bromine, a couple of drops of the bromine. And as you can tell, there's still that orange color that's present. So we're going to consider that no reaction, meaning no carbon-carbon double bond present. To the third test tube, I'm going to add some canola oil. And then I'm going to add a couple drops of the bromine solution. And as you can tell, that color, the orange color, is disappearing. And it may have just a slight tint, but we're going to call this, oh there we go, it looks like for all practical purposes that went back to colorless. So what does that tell us? That there had to be at least one carbon-carbon double bond present in there. Test tube 4, I'm using cyclohexane. drops of the cyclohexane, and to that I'm going to add the bromine. And you can tell that the color disappeared, meaning we've got that carbon-carbon double bond. Next compound is 1-octene. Add some of the bromine solution. And you can tell that the orange color disappeared there. Next compound is toluene, and toluene is an aromatic compound. It looks just like benzene, except the methyl group has substituted one of the hydrogens on the ring. So based on what we said earlier about benzene, we would expect nothing should happen here. So we've got our solution there of toluene, a couple drops of the bromine, and as you can see, that orange color has not changed, which is what we would expect for an aromatic compound, so no reaction there. And then the next two compounds we have unknowns. Now the thing about the unknowns is that there was a few compounds that gave positive results, there was a couple that gave negative results, so we can't really pinpoint exactly which of the knowns our unknown is, but we can tell whether or not it contains a carbon-carbon double bond. So this is unknown 1. Two drops of the unknown, and then to that I'm going to add some bromine. And it looks like the orange color has stayed. So again, we would say that's no reaction, no unsaturation present. And then for unknown 2, add a few drops of the unknown, and then some of the couple drops of the bromine. And you can tell that the orange color disappeared, so that would be indicative of a positive result, presence of a carbon-carbon double bond. I do want to say one thing in terms of what the lab book may ask or state, that if something was negative, they say to keep adding drops, or if it's positive, to keep adding drops. I don't really see the need of that, so if something's going to react, it does so fairly quickly, as you can see here with these. So I may not have followed the exact procedure that's in your lab manual, and I don't think it's necessary to count all those extra drops and go to 10 or 12 drops. I think you can certainly see if there was a result that was positive or negative here. One thing about the bromine I just want to draw to your attention, never use this outside the fume hood. You should always use it inside because it can be fairly toxic or hazardous. So always just make sure that you wear gloves, and that's true with any organic experiment. You always want to make sure you have your gloves, your safety glasses, and then always make sure you use the bromine inside the fume hood. So the second part of the experiment is to test the same substances that we use for the bromine test, but now we're going to treat that with potassium permanganate. What I have here is a test tube that is a control. This contains acetone, the solvent, and then a drop of the potassium permanganate, which has that purple color. So we're going to kind of keep comparing it to that during the experiment. So what I have to do for each of these, I'll need to put acetone into each of these test tubes. Acetone evaporates fairly quickly, so I'm going to do one test tube at a time. So I'll add about 1 milliliter or so of acetone to each test tube, and then I'll add a couple drops of our sample, and then we'll add a couple drops of the potassium permanganate, and then see what happens. First substance up for testing is cyclohexane. Add a couple of drops of that. Swirl it to make sure it's dissolved. And then we'll add a drop of that potassium permanganate solution. And you can see it has that purple color. So there's no change in the purple color. So that would be negative, meaning there's no carbon-carbon double bond there. Next sample we're going to use is the mineral oil. I'll need to put some acetone into that first to serve as the solvent. A few drops of the mineral oil. And then a drop of our potassium permanganate. And again, that purple color you see, so we would consider that no reaction. Third sample we're going to try is the canola oil. Add some acetone to the test tube, a few drops of our sample, and then a drop of the potassium permanganate. For the canola oil, you can kind of tell, you can certainly see that the purple color disappeared. And if you kind of look, you probably can see like a layer down at the bottom, which is our brown precipitate that's there. I added a little bit of cyclohexane just for solubility purposes, but you can certainly see that the purple color disappeared. Right, the next one is going to be cyclohexane. And it's always good to swirl the contents of the test tube there. I'm going to add a little bit more of the cyclohexane in case some of it got stuck to the side there. I think you can tell there is a difference in terms of the color of the blank test tube. If I kind of hold those side by side, you can tell that the purple color is disappearing. It's just taking a little bit of time, but certainly there is a color change there. This is the blank that has nothing but the reagent. So I'm going to come back to that, but you can certainly see that there is a reaction that's taking place. So that was with the cyclohexane. I'm going to say that's positive because there is a color change. The next one is 1-octene. You can see how purple it is when you start out with the reagent. And again, you can tell that the purple color is becoming more of a pinkish at the moment. That purple color is disappearing. I just want to kind of compare it. This is the one we did before that was the cyclohexane. You can certainly see that you can also see there's a brown material in the bottom. Again, it just takes a while. This one seems like it's heading in the same direction. So we'll come back and take a look at that, but you can certainly tell a difference between these two that we're starting with. Next sample is toluene. Take some acetone, put in the test tube. Drop of the KMNO4, and you can see that purple color is pretty, there really isn't much of a change in that purple. I want to go back to the one before. You can certainly tell the difference between those two. So I would say that the 1-octene is certainly a positive test. Looks like the toluene is negative. I don't see any change at the moment taking place. And then we have our unknowns, so we'll take a look at those. Put some acetone, followed by a couple drops of our unknown. I'm not seeing much going on there with that particular one. And then the last one we're going to test is the unknown 2. If I compare it to the toluene that we did before, looks like it is changing somewhat. You can certainly see that there is a difference in the color there. compared to what we started with. This one's getting much more lighter in color. That purple color is disappearing. But sometimes it takes, a few minutes for these to completely form that brown precipitate. I'm going to come back to this in a second. But when we were looking at these before, you can certainly tell the difference. This was the cyclohexane here, so you can see all that brown precipitate there. It takes a while for some of those to happen. Same thing for the 1-octane. Notice for toluene you still have that purple color. This one, you can tell certainly a difference between the two. This is that it's going to take a few minutes. And I may add just a little bit of that. Sometimes adding more of the sample will make that happen a little bit faster in case there's more of the reagent left over. But now you can really start to see. If I hold it up, you can certainly tell that purple color has disappeared. Okay, so what you would do is have all this recorded in your lab manual, and then future assignments based on this experiment will be assigned.